Welcome to Fundamentals of Artificial Intelligence. So far we have looked at the logical approach to AI, use first order logic to represent facts, and then use inference mechanisms to derive new facts from existing facts and rules. Under such an approach, the agent did not deal with any form of uncertainty in its domain of discourse. Today we will re-examine the very logical approach and see how it could be adapted to work for domains that have uncertain knowledge, domains that involve some form of uncertainty. So, this module is on reasoning under uncertainty. For reasoning under uncertainty, probability theory provides the basis for our treatment of systems that reason under uncertainty. We would look at utility theory that would provide ways and means of weighing up the desirability of the goals. One needs to remember that in an uncertain domain, actions are no longer certain to achieve goals. And therefore, we need mechanisms that would weigh up the desirability of goals and the likelihood of achieving them. And this we achieve through the utility theory. The probability theory and the utility theory come together to constitute what is called the decision theory, which involves ways and means of taking decisions within uncertain domain. And finally, we will look at how to build rational agents for uncertain worlds. In this lecture today, we would look at the basics of probability theory, including some form of representation for uncertain beliefs. It would cover the following 4 topics. We will look at acting under uncertainty. We will see what we mean by rational decisions. Thereafter, we would explore certain basic probability notations. And finally, we will look at the Bayes' rule. Belief networks, which are a very powerful tool for representing and reasoning with uncertain knowledge, will be covered in subsequent lectures. One needs to really understand that until now, any form of agent that we were dealing with was a logical agent. A logical agent believes a sentence to be either true or false. In these lectures that we start today, we would look at what are called probabilistic agents. Probabilistic agents are those that have a degree of belief about the validity of a given sentence, and the belief could be ranging from 0 to 1. So, let us first look at what do we understand by acting under uncertainty. Within a logical agent approach, agents almost never have access to the whole truth about their environment, and sentences can be ascertained directly from the agent's percepts, or others can be inferred from the current and previous percepts. This is done together with the knowledge about the environment. However, for almost every case, there would be certain important questions for which the agent can't find a categorical answer. This is where the agent must act under uncertainty. Uncertainty can arise because of incompleteness and incorrectness in the agent's understanding of the properties of the environment. Now, when we are talking of handling uncertainty, one needs to recall that if I am using first order logic to cope with complex domains like medical diagnosis or criminal investigation, or some form of methods and techniques to figure out faults in a system, there would be three main reasons why such first order logic systems would fail. One, we call it laziness. This is about too much work involved to create the complete set of antecedents or consequence needed to ensure an exceptionless rule. And it's too hard to use the enormous rules that result out of this. So if you are looking for completely covering one of these domains, then it would be too much of task, either to list the complete set of antecedents or consequence for a given rule, or it would be even hard to really get all the rules in the system. Number two is about certain ignorance, which is referred to as the theoretical ignorance. It is about the expertise of the area, which may not be sufficient to have complete theory for the domain that's being worked with. And finally, we have what is called the practical ignorance. Suppose we know all the rules, yet we may be uncertain about particular cases because all the necessary tests or evaluations may have not been or possibly cannot be done for that particular case. So agent's knowledge under such a situation can at best provide only a degree of belief in the relevant sentences. And that is why every sentence under such a scenario cannot evaluate to being just true or false. We have to associate to each sentence that the knowledge of the agent comprises of to a degree of belief. This is not only true for the medical domain that I have been emphasizing, it is also true for most other judgmental domains like law, business, design, automobile repair, gardening, so on and so forth. So dealing with degrees of belief is what is done through the probability theory, which assigns a numerical degree of belief between 0 and 1 to the sentences. Probability provides a way of summarizing the uncertainty, and one needs to realize that this uncertainty comes from our laziness and ignorance. Laziness here refers to our inability to completely quantify the domain, and ignorance here refers to either our theoretical ignorance of the domain or the practical ignorance when I am working with certain cases. So to make choices, that is to make rational decisions, an agent must first have preferences between the possible outcomes of the plans. And this is where we use what is called the utility theory. The utility theory is used to represent and reason with preferences. Here preference refers to options, choices and other alternatives of what is more preferred. Outcomes are completely specified state, and the utility theory is about figuring out which is more useful, or in terms we say the quality of being useful. So the theory says that every state that I get has a degree of usefulness or utility to an agent, and the agent will prefer states with higher utility. So let us now focus on the basic probability notations that we will use during the course of our discussion in this portion of artificial intelligence. So notation for describing the degree of belief is what is important. We need a formal language for representing and reasoning with uncertain knowledge. We use a version of probability theory, and we use propositional logic for its sentences, and the dependence on experience is reflected in the syntactic distinction between what we call the prior probability statements, which are statements which apply before any evidence is obtained, and conditional probability statements which include the evidence explicitly. So what we have here is some form of representation and that we have to create to capture the uncertainty, and that is captured in terms of the probabilities, and the statement itself is some form of propositional logic statement, but we associate to each of such statement some degrees of belief. And for experience, whether we have dependence on experience when we are trying to talk of the probability associated with a particular statement, is reflected in the way the statement is written. So for statements that have no experience of any evidence being obtained prior to the statement is being made, so those are called prior probability statements. And when we include evidence explicitly, we have what are called conditional probability statements. Now, when we are talking of such a representation, we have to talk of what is called the sample space. The sample space refers to the set of all possible worlds, that is, all possible outcomes, and we use the uppercase omega to represent the sample space. Omega is an element in the sample space. Phi is an event. Now this is interesting to realize that phi, the event or a proposition, is a subset of the sample space. Like, let's say I am rolling 2 dice and I want to figure out if every time I get a 11 between the pair of dices. So the event that I have is about the 2 dices adding up to 11, and that I could represent as pairs 5 6 and 6 5, because if one die has a 5, the other die shows a 6, I have 11, or the first one is a 6, the second one would need to be 5 to have an 11. So that would be an even, which would be from the sample space of all pair of dice that I am rolling. A probability model associates a numerical probability with each possible world. So every possible world must have a probability between 0 and 1, and then the total probability of the set of all possible worlds must be 1. Unconditional probability is when you do not consider any other information except for the object in question. Like, let's go back to our example of rolling a pair of dice. I have 2 dice, let's say one a red one, the other a blue one. Now in unconditional probability, I may only consider one, the red, and I would be not concerned about what is the result on the blue. Whereas in conditional probability, we have evidence, that is, we have information already revealed to us. So information that has been already revealed to us puts a lot of constraints on what could be the other possibilities. Like, coming back to the rolling of the 2 dices that I was talking about, let's say I am talking of a sum for the 2 dices. Now if I see my red dice has a 6, immediately I know that the sum of the 2 dice cannot be less than 6. That is, it cannot be 5. And those type of scenarios is what we have under conditional probability, where we have evidence or extra information already revealing to us what could be the possibilities remaining with us. Now, coming back to the two probabilities, the unconditional probability is also referred to as prior probability. So, the notation used for it is P of A for the unconditional or prior probability that proposition A is true. For example, if fever denotes the proposition that a particular patient has a fever, then I can write probability of fever is equal to 0.1, means, so when we are talking of unconditional or prior probabilities, we need to understand that it is in the absence of any other information. So, under such a scenario, the agent will assign a probability of 0.1, which is a 10% chance to the event of the patient having a fever. On the other hand, we need to understand that conditional probabilities will have certain information. So, unconditional probabilities can only be used when there is no other information. As soon as some new information B is known to us, we have to reason with the conditional probability of A given B instead of the prior probability. We will come back to conditional probability in a minute. Before that, let us look at what we understand by random variables. The proposition that is the subject of a probability statement can be represented by a propositional symbol. As in the previous case, I wrote probability of A being a propositional symbol. Propositions can also include equalities, and when they include equalities, they involve random variables. So, every random variable has a domain, a set of possible values that it can take. For example, let us say we have the random variable total that calculates the sum of the two dices. Then the domain is the set 2 up to 12, because 2 dices can maximum add up to 6 plus 6, 12. So, on the other hand, a Boolean random variable has the domain of either true or false. For propositions involving random variables, for example, if we are concerned about the random variable weather, we might write statements like the probability of weather being sunny is 0.7, or the probability of the weather being cloudy is 0.08. We can also view proposition symbols as random variables if we assume that they have a domain that's true or false. For example, recall the expression that we have used, probability of fever. Now, probability of fever can actually be viewed as a shorthand for probability of fever equal to true. Similarly, probability not fever could be actually representing probability fever equal to false. So, we can see that even propositional symbols can be viewed as random variables. A probability distribution is when we want to talk about all the possible values of a random variable, and it is usually indicated by a boldface P. We could have what is called a discrete random variable, which is a random variable that takes a finite number of distinct values. So, an expression such as probability of weather, I could denote a vector of values for the probability for each individual state of the weather. So, it could be like probability of weather being sunny, cloudy, rainy, or some other options. Now, this statement defines a probability distribution. because it gives us all the possible values of a random variable. On the other hand, if I have variable which is called continuous random variable, a continuous random variable is one that takes an infinite number of distinct values. For example, I could be talking of the temperature. So, the probability of temperature being uniformly distributed between 18 degree and 23 degree is called a probability density function. So, a continuous random variable, when I am talking of and trying to express what its value would be over the complete distribution, it is a probability density function. But when I am talking of a discrete random variable and talking of all the values of the variable, then it is a probability distribution. Let us now come back to conditional probability. Conditional probability is also called posterior probability and is expressed by the notation probability of A given that all we know is B, or read shortly as probability of A given B. It is about having some evidence concerning the previously unknown proposition making up the domain. So, when I have such information or evidence, then prior probabilities or what we call the unconditional probabilities are no longer applicable, and this is where I have to take help of the posterior probabilities. For example, here is a probability of cavity given toothache. So, indicates that if a patient is observed to have a toothache and no other information is yet available, then the probability of the patient having a cavity will be almost 80%. So, probability of cavity given toothache is 0.8. Now, this probability that I have written here has some evidence concerning the previously unknown proposition making up the domain, and therefore, under the observation that the patient is supposed to have toothache, the probability of the patient having cavity is a conditional probability. So, conditional probability, probability of x given y, is a two-dimensional table which gives the value of xi's and yj's for each possible ij pairs. Conditional probabilities can be also defined in terms of unconditional probabilities. Like here, I have the probability of A given B written as the probability of A intersection B by the probability of B. This equation can also be written as probability of A intersection B is probability of A given B into probability of B. This is called the product rule, and we will come back to this during our course on discussion of reasoning using uncertainty. So, the product rule is perhaps easier to remember if you think in the following lines. It comes from the fact that for A and B to be true, we need B to be true, then A to be true given B. So, that is the product rule. To define properly the semantics of statements in probability theory, we would need to describe how probabilities and the logical connectives interact. We have looked at the semantics of the logical connectives during our discussion on knowledge representation and reasoning. Here, we will look at how does the probabilities interact with the logical connectives. The first axiom of probability states all probabilities are between 0 and 1. Now, necessarily true, that is valid propositions, have probability 1, and necessarily false, that is unsatisfiable propositions, have probability 0, in the sense that the probability of true is 1 and the probability of false is 0. The third axiom of probability is the following. It gives us the probability of a disjunction. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So, let us try to understand this with a small figure. But prior to this, we need to take note that the first two axioms of probability serve to define the probability scale. The probability of disjunction can best be understood by looking at this figure, where each proposition is shown as a set, and this can be thought of as the set of all possible worlds in which the proposition is true. The total probability of A or B is seen to be the sum of the probabilities assigned to A and that assigned to B, but we need to subtract from it the probability of those cases that lies in A and B, so as those cases are not counted twice. So, we have PA plus PB, but these cases which are A and B, I have to subtract them to ensure that I do not double count them. So, from these three axioms, we can derive all other properties of probabilities. For example, if we let B be not A in the last axiom, we obtain an expression for the probability of negation of a proposition in terms of the probability of the proposition itself. Let us look at the derivation here. So, I have the probability of A or B, but now I have replaced B with not of A. So, I have probability of A plus probability of not of A minus probability of A and not A. Now, this is where we need to understand the logical connectives. Probability of A or not A is going to be 1, because that is a tautology which is always true, and therefore, I have 1. The probability of A and not A, so this was a disjunction, A or not A, it is going to be true always, therefore, giving me a 1. Whereas, on this side, if you see, probability of A and not A is a contradiction, going to be false always, and therefore is 0. So, what I have finally is 1 equal to probability of A plus probability of not A, and from that I can write probability of not of A is equal to 1 minus probability of A. So, the probability of the negation of a proposition in terms of the probability of the proposition itself comes out as a consequence of the three axioms that we have written. From these three axioms, we can derive other properties of probabilities as well. So, now let us try to define something called the joint probability distribution. A joint probability distribution completely specifies an agent's probability assignment to all propositions in the domain. So, it assigns probabilities to all possible atomic events. Here, I have an n-dimensional table with a value in every cell giving the probability of that specific state occurring. Now, coming back to this toothache and cavity problem, I could think of cavity and not cavity, toothache and not toothache, and completely specify the probability assignments, and this would be a joint probability distribution. Now, there are certain things that needs to be understood in a joint probability distribution. The first one is that we are talking of atomic events. Now, atomic events are mutually exclusive. So, any conjunction of atomic events is necessarily false, and because they are collectively exhaustive, their disjunction is necessarily true. Hence, from the second and third axioms of probability, the entries in the table sum to 1. And the joint probability distribution can be used to compute any probabilistic statement. Like adding across a row or column gives the unconditional probability of a variable. Like for the probability of cavity, all I need to do is add up whether it is too thick or whether it is not too thick, because I am talking of the unconditional probability of cavity. So that I add up the row. Or for that matter, if I am looking for only the toothache, I would add up a column. When I am looking for a probability of cavity or toothache, I would add up values of cavity 0.04 and 0.06 and 0.01, which is a probability of toothache. Now recall that this is unconditional probability. So here toothache doesn't matter whether I have a cavity or do not have a cavity. Both of them needs to be added up. On the cavity, it doesn't matter whether I have toothache or no toothache. Both of them needs to be added up. So when I am looking for conditional probabilities can be found from the joint as well. So this is something that I need to mention here, that the joint probability distribution is also referred to as joint simply. So here is a conditional probability of cavity given toothache. So that too I can find out from the joint probability distribution, which is probability of cavity and toothache and probability of toothache. If you remember the product rule that we were discussing a little while ago, that could lead me to conditional probabilities from the joint probability distribution. Now let's recall the two forms of the product rules. Probability of A and B is probability of A given B, probability of B, and probability of A and B can also be written in terms of probability of B given A and probability of A. So equating the two right hand sides and then dividing by PA, we could get that the probability of B given A is actually probability of A given B multiplied by probability of B whole divided by probability of A. This is an equation which is known as the Bayes' rule, also called the Bayes' law or the Bayes' theorem. This simple equation surprisingly underlines all modern artificial intelligence systems for probabilistic inference. Now, just at its simple first look, one fails to understand the power of the Bayes' rule. Let's try to understand why it is so important for probabilistic reasoning with an AI. The Bayes' rule requires three terms. If you have noticed properly, two of them are prior probabilities and one of them is a conditional probability. These three computes the fourth, which is a conditional probability. In practice, the Bayes' rule is very useful because we have good probability estimates for the three quantities that I have listed above. Now let's take an example and try to understand the application of Bayes' rule to a very simple case. This is an example from Russell and Norwick's book. So here we have a statement which says a doctor knows that the disease meningitis causes the patient to have a stiff neck, say 50% of the time. The doctor also knows some unconditional facts. One, the prior probability of a patient having meningitis is 1 over 50,000 and the prior probability of any patient having a stiff neck is 1 over 20. Let S be the proposition that the patient has a stiff neck and M be the proposition that the patient has meningitis. Now, probability of stiff necks given M is 0.5 it's 50%. That's what it says. Stiff neck because of the disease. Probability of the disease itself is 1 over 50,000, and that's a prior probability, unconditional. And then I have a probability of stiff neck, which is 1 over 20, 0.05. Now, if one wants to know what is the probability of the disease that he has a stiff neck, then the probability is 0.0002, which is very low. Notice that even though a stiff neck is strongly indicated by meningitis, which is a probability of 0.5, the probability of the disease in the patient with stiff neck remains very small. This is because the prior on stiff necks is much higher than that of the disease itself. Now, this was a very simple application of the Bayes' rule to understand what would be the probability of the disease given stiff neck. But Bayes' rule can also be used for combining evidences. Like suppose we have two conditional probabilities relating to cavities. One saying the probability of a cavity given a toothache is 80%, and the probability there is a cavity because the dentist could catch it with his probe is 95%. Now, what can a dentist conclude if it catches the aching tooth of a patient? That is, what is the probability of cavity if I have toothache and a catch, given toothache and a catch? Now, this is what the probability would look like. Probability of toothache and catch given cavity, probability of cavity, probability of toothache and catch. One needs to realize that although it seems feasible to estimate conditional probabilities for n different individual variables, it is actually a daunting task to come up with numbers for n square pair of variables. And therefore, application of Bayes' rule needs to be simplified to a form that requires fewer probabilities in order to produce a result when combining evidences. So, the process of Bayesian updating, which incorporates evidence, is done one piece at a time, modifying the previously held belief in the unknown variable. So, if I was talking of cavity, toothache and a catch together, I would first look at cavity and a toothache and then look at the other one. So, when catch is observed, we can apply the Bayes' rule. At that point, toothache is the constant conditioning context. What it means is that I would be looking for definitely the toothache and catch, but when I am doing it, I would be looking for the cavity and toothache, and the probability of cavity and toothache will be brought from here into this equation of the Bayes' rule here. So, in Bayesian updating, as new piece of evidence is observed, the belief in the unknown variable is multiplied by a factor that depends on the new evidence. So, the cavity, if you think of this in this way, that the cavity is the direct cause of both the toothache and the probe catching in the tooth. Given a cavity, the probability of the probe catching does not depend on the presence of a toothache. Similarly, the probe catching it is not going to change the probability that the cavity is causing a toothache. So, all of this is about exploiting causal relationship in the domain between these variables. and that is called conditional independence. So, you exploit what is called conditional independence of toothache and catch given cavity, and given the conditional independence, we can simplify the equations for updating. Combining many pieces of evidence may require accessing a large number of conditional probabilities, but nevertheless, conditional independence, which as I mentioned before, is brought about by the direct causal relationship in the domain, allows Bayesian updating to work very effectively even with multiple pieces of evidence. This is what we have for today. So, let us quickly recall what we have done before we move on to something called the Bayesian network in the next lecture. So, today we looked at uncertainty and realized that uncertainty arises because of both laziness and ignorance. It is inescapable in complex, dynamic or inaccessible worlds. Now, many of the simplifications that are possible with deductive inferences are no longer valid when we are talking of domains with uncertainty. Probabilities express the agent's inability to reach a definite decision regarding the truth of a sentence and summarizes the agent's belief. Basic probability statements we have seen include prior probabilities and conditional probabilities. We have looked at the axioms of probability, which specify constraints on reasonable assignment of probabilities to proposition. An agent that violates the axioms actually will behave irrationally, and the joint probability distribution that we have seen specifies the probability of each complete assignment of values to random variables. It is usually far too large to create or use, and we have looked at the Bayes' rule, which allows unknown probabilities to be computed from known stable ones. And finally, we have looked at conditional independence, somehow allowing Bayesian updating to work effectively even with multiple pieces of evidence. Thank you very much.